Hey everyone, welcome to the talk on achieving the ultimate performance with KVM. First, a few words about me. I'm the Chief of Product and a co-founder of Stor Pool. I have 20 years of experience in ISPs and software-defined networking, and for the last 10 years in software-defined storage. My whole career has been focused on IT infrastructure and especially on inventions and performance and efficiency. Our company does an NVMe high-performance software-defined storage, which is used mostly for virtual machines and containers. It's a scale-out system with high availability. It's API controlled, and our solution is mostly used for virtual disks for KVM virtual machines, and hence this talk and hence our large experience in optimizing KVM environments. It's also used for bare metal Linux hosts as well as for VMware and Hyper-V and Zen server and other block storage use cases. And in most cases, it's delivered as a fully managed service with monitoring and analytics and metrics collection with hundreds of thousands of metrics per second that we collect and analyze. And it's deployed on thousands of servers in hundreds of availability zones. So it's a kind of fairly good scale, which means a lot of automation and also means a lot of experience in terms of different environments and how it behaves in these different environments. Why does performance matter? Why should we care? First of all, it's because of better application performance, not because of the performance on a particular synthetic benchmark. So it's things like the time it takes to load a page or to answer a particular API call, the time it takes to rebuild a system. So if you're in a development environment, the time building and testing is like what determines your, in a lot of cases, your kind of iteration cycle. The time it takes to execute a specific query in the case of business analytics or big data, right? So in cloud and multi-tenant environments, it means KPI customers. And in purely business metrics, performance may translate into a shorter return on investment, better return on investment, and lower total cost of ownership. So in public clouds, it means you can win customers over from your competitors. Performance means that. And in private clouds, it means you can do more with less, meaning on the same in the same data center, on the same servers, you can do more work with the existing servers. You can win applications and workloads from your competitors, which in the case of private cloud, it's mostly public cloud, right? So my agenda for kind of ultimate performance with KVM is to go through the hardware, compute or like CPU memory virtualization, networking and network virtualization, storage virtualization, and at the end I'll draw a very short conclusion from what we've learned here. So in hardware optimization, compute node hardware is one of the kind of most expensive and determining components on getting the best total cost of ownership or the best performance out of your investment. And the usual optimization goal there is to get the lowest cost per delivered resource at a fixed performance target. And something that's very important in this area is to calculate all costs, which means the power, cooling, space, servers, network, and the maintenance of this environment, which includes kind of salaries and services. So for example, our goal may be what is the cost per delivered virtual machine with 4 dedicated vCPUs, a 3 GHz particular generation cores, and 16 gigs of RAM. So, make sure you know your optimization goal before you start optimizing. A more unusual optimization goal we see sometimes is what is the best single thread performance you can get at any cost. We see this one fairly rarely in some say algorithmic trading or other very latency sensitive applications, right? And an unusual optimization goal usually leads to an unusual outcome, right? So how do you do this optimization? Well, you make a very large spreadsheet which takes inputs such as the cost of power, how much power can you fit in a rack, what is the cost of a particular server model, what is the cost of the CPU, etc. And in this spreadsheet, you have you could have, say, 100 rows for every different option you're evaluating. And for every option, it will spit out a number, and that number in this case is like total cost per core. That is the total cost per core, including memory and everything else I mentioned. So it's not just the core, it's the whole data center associated with that CPU core. So if you change the input parameters, the ordering of these CPUs changes as well, right? So some outcomes with kind of parameters we've used, like cost of power, etc., these are the best Intel CPUs for particular performance level. So if you need a kind of slightly faster cores, you would pay something like 25-30% more per core if you need that like additional performance per core, right? And for AMD CPUs, these come up on top based on our input parameters. Obviously, if you change the input parameters, the order changes, right? Then on to compute form factor. Both are absolutely valid. So which is the optimal depends on external parameters. So these are like power density per rack. So these are large compute nodes, which are 2 rack units, and at the other end of the spectrum, you may have 2 compute nodes per rack unit. So extremely high density of compute, but also power density. Further on compute hardware, there are things which might affect application performance are firmware versions, BIOS settings. You need to, one thing that affects it a lot is power management settings in servers. So things, so you need an understanding of C states and P states and hardware P states and the so-called performance bias. And it's quite different how these things work on AMD CPUs versus Intel CPUs. So they have a different way of controlling the power of the processor. And something to keep in mind is you need to think of rack level optimization. So instead of trying to optimize the cost and performance of an individual server, what you're trying to optimize is kind of the total solution cost, which requires you to look at least rack level, if not data center level optimizations, right? The next section is on virtualization and CPU and memory. So tuning KVM, there are some good guides out there. We, like a couple of years ago when we started looking into these things, this guide was very helpful to us, and you can also use that as a kind of a baseline. It's becoming slightly outdated nowadays, and you may be able to find better resources out there. And something that's really important, don't trust everything you read. So the approach where you go out there and find someone claiming that a particular knob improves performance, it doesn't translate well into your environment. So you need both your specific workload, your specific optimization criteria, like what are you trying to make better, as well as how these changes translate work in your specific environment. The reason for that is the systems we are working with here are complex systems, so it is very hard to predict an outcome in these systems. Even if generally something is a good idea, it may lead to worse performance in your environment. So make sure to run your own benchmarks. Generally, on Red Hat-based distributions, so like CentOS and Red Hat Enterprise Linux, there is tuned, and tuned virtual host does most of the things that were mentioned in that Red Hat virtualization optimization guide that I mentioned on the previous slide. You need a recent Linux kernel, KVM and QEMU, because there are a lot of performance improvements over the years in the Linux kernel. But at the same time, try not to trade performance for reliability. So you need to find a balance where you're not running the absolute bleeding edge, because there are a lot more issues in there. You need to run a version of the kernel and QEMU and KVM, which are tried, which have been tested by a large community before you get to use them, right? And QEMU KVM EV is an example packaging of QEMU and KVM that achieves that for us. So on CPU, the typical approach is to have oversubscribed CPU instead of dedicated CPUs. Because most virtual machines are idling. Now this kind of is a generic statement, and it depends on your workload and kind of the service you're selling to your customers. So in terms of, say, in public cloud, they're both services which are at lower price and they rely on CPU oversubscription to achieve the economics. And there are also services which are with dedicated CPU. So both exist. Hyperthreading is used. NUMA optimizations are used quite extensively. So things like both in Intel and in AMD CPUs, achieving data locality so that the virtual CPUs run on CPU cores which are close to the memory used by these virtual CPUs. Gives you a very high performance boost. And there are some consequences of that. For example, you can't have VMs which are larger than a single NUMA node in terms of amount of memory they need and amount of CPU they need. Inherently get a lot worse performance because they're spread across NUMA nodes. And interrupts, so you have the host and virtual machines. So interrupts for network and storage adapters need to be routed to NUMA nodes that they reside on. So these like hardware devices like network interface cards are on a particular NUMA node, and getting their interrupts on that node, it gives you a large performance boost. Also, getting these noisy things like background processes in the host operating system, make sure that they don't run on the same CPUs where your virtual machines run. You can kind of separate the cores of the host between cores used to run client workloads like virtual machines and cores used to run your infrastructure, things like networking and storage and anything that you run in the host operating systems. And as I mentioned, the more unusual architecture goal is to use CPU pinning, which gives you significant performance gain, but is also quite expensive, right? So one thing to understand in compute is to understand the difference between oversubscription and congestion. Oversubscription by itself is not bad for performance. So oversubscription only means that we've provisioned more virtual machines that we have physical cores for. But if all these virtual machines are idle, all virtual machines are idle except for one which is active, then no one would notice that we've over-provisioned our CPU resources. And there are metrics that the Linux kernel exposes, which you could use to tell the difference, to tell when there is really CPU congestion. And please understand that even at a fairly low CPU load, like 20%, there may be a lot of CPU congestion, and also even if you have 100% CPU load, there may be zero CPU congestion because they're dedicated CPU cores. So our approach to this has been to measure CPU congestion. The way we measure it is we sample this kind of scheduler statistics in the host kernel. This is an example for how something like that looks like. So these, in different colors on this chart, you have individual compute nodes. And you can see that there are these large peaks every 5 minutes. These are cron jobs in the guests, caused by cron jobs in the guests. And on this chart, 0 means no congestion. There is, so 100% CPU load is at 0, right? And then 100% means for every CPU core, you have one process executing, and in addition to that, you have an additional process waiting. 200% means one process executing and 2 more processes waiting for execution for CPU resources, right? So in an ideal world, this should all be 0, but you know, it's not such an ideal world, and you can use this metric to do things like rebalance your virtual machines. So take virtual machines from the host that experience CPU congestion and move them to hosts that don't. This is a much better metric than CPU utilization because this is what your customers experience as steal time and not CPU utilization in the host. So on to memory. In memory, the typical approach is to have a dedicated RAM and to get slightly better memory latency memory performance by using huge pages or transparent huge pages, NUMA optimization, as I mentioned, and good rule to use local memory, NUMA local memory for your virtual machines if you can. More unusual cases, oversubscribed memory with KSM, and this conflicts with huge pages, so you can do either this or that. You know, there are choices that you need to make, either optimize for cost and reduce memory usage, or optimize for not so much for cost, but more for performance, and you use huge pages and things like that. Our next section of the presentation is about networking. So in networking, again, you have 2 different approaches. You'll notice it's a recurring theme in this presentation. There are multiple ways to do things, and they have their benefits and drawbacks. So in networking, you could either do virtualized networking, which means that the packets of the virtual machine get processed in the host in some way, for example, doing bridging or firewall or shaping, etc., in the host operating system before they're passed to the physical network underneath. And the alternative approach is to do pass-through networking, which means the packets of the virtual machine are handled directly by a network interface card in the host, and the host kernel doesn't see these packets at all. They just go directly between the guest kernel and the network interface card. So you have hardware emulation, and these are fairly kind of old and slow approaches to doing virtual networking. Nowadays, the driver model or the device type we use for virtual networking is virtio-net. There are regular virtio versus vhost-net versus vhost-user, and I have a couple of diagrams to show what the difference is. And then in terms of how you process these packets, you could use Linux Bridge or Open vSwitch in kernel or Open vSwitch in user space with Open vSwitch DPDK. So this is how they look like. This is the most basic one, which is virtio-net emulated device in the QEMU process. You have the virtio-net driver in the guest, communicates with virtio-net device backend in QEMU, which then goes through a tap device in the host to submit the this is like a software interface in the host to submit the packets to Linux Bridge or Open vSwitch in kernel in the host. So this is the kind of most traditional and also default out of the box way QEMU KVM implementations are configured. It's obviously much more efficient than emulated hardware virtio has been designed for this. Next alternative is QEMU bypass. So you do the virtio-net driver in the guest communicates directly to a vhost-net backend in the Linux kernel. The QEMU process, QEMU only takes care of setting this up. It doesn't. The communication between these two is over shared memory, and so the QEMU process is not involved at all in the communication between the two, except for the so-called kicks, which is like waking up a virtual machine to when there is an interrupt. So in this case, there is the vhost-net kind of thread in the kernel, and that submits packets over the tap device to Linux Bridge or Open vSwitch in kernel. Next alternative is vhost-user, and that gives you the virtual machine communicating over shared memory with another process, user space process in the host. That user space process may be Open vSwitch DPDK, and this gives you kind of there are no because Open vSwitch DPDK communicates directly with the network interface card. This achieves kernel bypass by virtual machine communicating to the Open vSwitch DPDK process, which then communicates directly to a network interface card. Drawbacks, this process needs a dedicated CPU core or more, depending on how much performance you need. The positive of this is there is a very large throughput and latency difference between the previous approach and this one. And lastly, you have PCI Passthrough. In this case, there is a kind of a network interface card driver directly for the hardware of the host. This is achieved using SREcon20 and VFs in the network interface card. Drawback of this approach, no live migration and no virtual networking features like filtering or shaping or etc. Right. This is how the different virtualized approaches look like in our tests in our lab. So virtio-net, which is kind of the default nowadays, gives you about, say, 90 to 100 microseconds latency between virtual machines on the same host. virtio-net with vhost with Linux Bridge gives you about 37. virtio-net with vhost-user with Open vSwitch DPDK gives you about 14 microseconds round-trip latency between two virtual machines. The way we measured this was using this command. A bit more on kind of how they look like in terms of processes. So the kind of most traditional one, this is the vhost thread in the kernel. So in a loaded situation, you have CPU consumed by your kind of load application and your virtual driver in the QEMU process down here, as well as CPU consumed by the virtio-net backend, the vhost backend thread in the kernel. Right, so this is kind of in kernel thread. this is this approach. So in this approach, you get CPU used by the KVM virtual machine. So this is the kind of the workload and the virtio-net driver, and CPU used by open vSwitch. And remember, this is in kind of a loaded case. In this approach, there is always kind of a dedicated CPU core, which you've set aside for virtual networking, right? Some additional reading on virtual networking. So this is virtual networking with vhost-net and open vSwitch with DPDK support. Our last section is storage. So on storage, again, there are two approaches. You have virtualized storage, which means the storage requests are processed by the host operating system in some way. And you have full bypass. So for example, if you have an NVMe device in the host, you could pass the whole device to a virtual machine. Or if the NVMe device supports VFs, you could pass like a part of an NVMe device directly to a particular virtual machine. But what you only get speed with that, and you don't get live migration, and you don't get high availability or any other data management features such as snapshots or theme provisioning or cloning, etc. Right? So most common approach is to use virtualized networking because it gives you live migration and high availability. So in virtualized networking, nowadays the default is that there is no block caching in the host operating system. So this tells the QEMU process to use direct I/O and completely bypass the host buffer cache. There is, it uses nowadays using IO native, which is to use Linux native AIO instead of POSIX threads, POSIX AIO, which is threads IO. The driver or kind of virtualized device we use for storage nowadays is virtio-block or virtio-SCSI. Both exist and they have some pros and cons between them. Virtuo-SCSI, the most significant benefit of using that is kind of compatibility with all kinds of software in the guests, which assumes that all devices are SCSI devices, which yeah. And virtio-block has a slight kind of latency and performance advantage, but they're very close. So usually it's not because of performance you would choose one or the other. There is this concept also in QEMU that I/O could be submitted to the host not using kind of the QEMU main process, but from a separate I/O thread, which is a kind of a dedicated thread in QEMU to do that. So this would be kind of the 2019-2020 default and best current practice for how to configure QEMU for performance. And things coming out in 2020 with very new kernels is something called IOU ring, and I really think they need to change the name of this new technology because it has a huge potential and it's growing in popularity and scope, but the name is awful. So the difference is like this. So instead of the QEMU process using direct I/O, Linux native I/O, to get to the host kernel, the QEMU process can use this new mechanism in the Linux kernel, which is very similar to vhost. Sorry, it's similar in some ways to vhost in that it uses shared memory between the two communicating parts between the QEMU process and the kernel. But it is a more modern implementation with a lot of kind of 10 plus years of learning of how to design a high performance interface between two processes, right? So IOU ring between the QEMU process and the kernel, and this gives you a kind of lower latency, higher throughput between the two. And then there is even further down the line, and not ready for production use, in my opinion, there is this idea of IOU ring pass-through, in which the guest kernel can talk directly to the host kernel without going through the QEMU process. Which saves this is the ultimate goal, which saves context switches and kind of gives you context switch less processing of storage operations. In this one, you still have, so guest kernel submits IO to the QEMU process. There is a VM exit, and in the QEMU process, there is submitting the IO to the host, right? Linux native IO also has context switches to get from the QEMU process to the kernel, but these may be, say, grouped for many IOs, and that is somewhat optimized. So this saves context switches between QEMU and the host kernel, but doesn't remove the context switches between the guest and QEMU. And an alternative approach, so if you remember in networking, I mentioned that vhost-user with vswitch-DPDK, for example, for packet processing, can give you the kind of lowest latency and highest throughput. A similar approach works with block storage. So instead of guest kernel, host kernel KVM to QEMU process, host kernel submitting IO to the storage initiator, whatever that is, right? So that may be like a nice cozy initiator in the kernel, or it may be user space processing operations, right? With vhost-user, you could get guest kernel talking directly to a storage initiator. And this is the approach we use in StorPool to achieve very high performance for KVM guests. It's not the only way, the only thing we do to achieve high performance, but this is one of the tools in our toolbox, right? So this is kind of an overview of the StorPool architecture. On one end, you have StorPool server instances, which use a dedicated CPU core. They talk to NVMe drives using a POL mode driver, so there are no context switches here. We talk to a network interface cards using a POL mode driver, so kernel bypass, there are no context switches for through there. So from a KVM virtual machine, if you submit, for example, a read operation, that operation goes through the kind of the StorPool initiator through the network interface card, network interface card, StorPool server instance, NVMe drive, and the data gets back without a single context switch. And the result is we can kind of, depending on the speed of the network and kind of speed of CPUs, etc., we can read data from an NVMe device, which is remote, in about 70 or 100, between 70 and 100 microseconds. And one of the things that enables this is the vhost-user mechanism I mentioned, which exists in KVM. There's just not other implementations of it in storage initiators. And the Linux kernel community seems to be moving in the direction of IO U-ring and IO U-ring bypass, while the vhost-user mechanism already exists in KVM, right? So to understand how to measure storage performance, there are a few things to look at. Lots of snake oil out there, so if you see a published benchmark, you should look at that with a grain of salt. For example, the hardware configurations they would use in their tests are totally unlike the hardware configurations you would use for your production environment. They would do synthetic tests with kind of huge Q depth, because that's the test that gives them the highest numbers to brag about, right? And they would test with, say, a RAM disk backend, because no one is looking at these things when they read benchmarks. And most importantly, synthetic benchmarks don't approximate the real world performance, or they help to figure out the performance envelope of a particular system, but they don't translate directly into application performance, right? So important to understand, every transaction processing system has like a latency versus operations chart, or that looks something like this. If you have low a low load, you'll get the lowest latency. If you increase the load, you get a slightly higher latency and you get the lowest cost per delivered resource, but you don't want to run your systems at that level, say at 90% of their capacity or performance throughput capacity. Because once you get over this, you get only pain. And only pain is when you start getting a lot of operations piling up. So you have a system that can do 1,000 operations per second and you demand 1,100 operations per second from it, you'll get an infinite queue. So there will be operations piling up and you get latency of several minutes because these operations need to be, or errors alternatively. And what published benchmarks tend to do is they tend to go to the right end of the scale, which is totally unlike what it is in a different mode of the system. So this would be in congested mode, and this would be in elastic mode. In production, you would run your systems in elastic mode. Published benchmarks tend to run systems in congested mode. A quick example of that, so this is kind of a real storage system, and this is what an IOPS benchmark would measure. And your real application load would be in that part of the curve, assuming you have enough throughput, obviously. And would changing that number affect application performance? Usually not. So it would only affect application performance if it's not enough. Once you have more throughput than you need, changing the throughput doesn't affect application performance. But changing the latency always affects application performance. So this is the area that we have been focusing on. And as an example, these are some tests we run in various public clouds, and we have a detailed report on how we did that to make sure it's fair to everyone. And you can see in virtual machines, which are very similar cost, the same amount of CPU, the same amount of memory, you get a vastly different application performance, in this case of the PostgreSQL database. So for example, you could, for 2,000 transactions per second on that, 2,000 transactions per second on that benchmark, you get 1 millisecond per transaction latency versus average versus say 3 milliseconds in the second best cloud. And this translates to, like, you can see very similar patterns in a lot of different types of applications, and also database performance translates into kind of shorter responses for API calls, higher throughputs of an API server or a microservice, etc. Yeah. So, in conclusion, KVM has the right tools to get very good performance. In our experience, the defaults are already pretty good, but if you want to get that, extra bit of performance, and if you want to make it from really good to exceptional, you need to turn a few knobs. You need to kind of configure it in the right way. These are the systems, so IT infrastructure, virtualization, networking and storage. They are complex systems, so it's very hard to guess from a description of a system. It's very hard to guess what kind of performance, application performance you would get out of it. So the only proper way to do it is to measure, right? To measure what matters to your team and to your company, which is unlikely to be an IOPS number, right? It's quite likely to be something very different than that. And if you work with partners who understand performance, like Stor Pool, you can gain a lot, and you can gain a lot not just in kind of getting application performance numbers to brag about, but you can gain a lot in terms of saving time for your team, as well as in terms of getting better application performance, which translates into better overall productivity for your development team, as well as better total cost of ownership of your infrastructure. So doing more with less money, right? And this was my presentation. Thank you, and let me know if you have any questions.